Let's see now how atoms combine to form molecules. American chemist Gilbert Newton Lewis, who was a professor at UC Berkeley, proposed in 1915 that all elements wish to achieve the electronic configurations of noble gas because these configurations, according to him, possessed unusual stability. And all other elements were striving to achieve that stability by either giving up electrons or accepting electrons or sharing electrons with other elements to get to the most stable configuration of electrons. This theory is called the Octet Rule because neon or argon or so on have 8 valence electrons in their final shell. Okay. To get to that stage, elements can either give up or take their electrons or share them more or less evenly with other elements, which then determines two main bonding classes. The first one is Ionic bonding, and this is the class where atoms of elements give up electrons or accept electrons from other atoms. In other words, this is characterized by complete electron transfer. If you look at a lithium, which has only one electron, so it's very close to the configuration of a noble gas, and fluorine, which has 7 electrons, so it's also very close to the configuration of a noble gas, then what we'll see is that lithium gives up this 1 electron to fluorine to result in lithium plus, since now it's 1 electron short, and fluorine minus, which now has 1 more electron than it was supposed to. These two species are ions, and they attract each other by Coulomb forces. And this is the so-called ionic bonding. So lithium plus now has an electron configuration which is equal to that of helium, whereas fluorine minus now has electron configuration which is equal to that of neon. And so this is one way to get to the electronic octet. Okay? The other version, which many other elements practice, is a so-called covalent bonding. And you see already covalent, co indicates some sort of cooperativity and cooperation. It indicates sharing of electrons. And here there is no complete electron transfer, so atoms just share electrons. For example, if we have hydrogen, which has 1 electron, and it meets another atom of hydrogen, which also has 1 electron, they come together and they have these 2 electrons between them. So now that this hydrogen has an electronic configuration of helium, and this one also has an electronic configuration of helium, because they share each other's electrons. Now the question is, which one is it going to be? Which atoms ionically bond? And to answer that, we have to look at the properties of individual atoms in the ionic or covalent bond. Some things are pretty straightforward. For example, if in the example I've just shown you, the 2 hydrogen atoms, it's pretty clear that these two have to share their electrons because they're exactly the same. So there is no reason why these electrons would go towards one hydrogen more than to the other. And so this bond is going to be covalent for sure. And it's also going to be non-polar covalent, since there is not going to be any part of this molecule which is going to be more electron-rich than the other. On the other hand, if we have a carbon atom, which is forming a bond, again by sharing electrons with chlorine, then these two electrons are going to be a little bit closer to chlorine. And you might ask, well, why? The reason for this is that chlorine needs only one electron to achieve the stable configuration of a noble element, whereas carbon needs 4. So chlorine, in a way, is a little bit more desperate for that one electron, so it holds to it a little tighter than carbon does. But they're still shared, and so this bond is called covalent, but polar. Okay? Now the final case is the one that I've shown at the beginning of this section of lithium fluoride, but we can look at a different example of sodium chloride. And here, sodium needs to release one electron to get the noble gas configuration, whereas chlorine needs to accept one electron. So chlorine is really desperate to get an electron. Sodium is really desperate to give up an electron. So they really have no interest in sharing these electrons. They just want to transfer it completely. And so this is really a win-win situation, and this is called the ionic bond. And what you will notice is that elements on the left-hand side of the periodic table, such as sodium or lithium, tend to engage in ionic bonds with the elements on the far right of the periodic table, such as chlorine or fluorine. And so these extremes on the left and right will be ionic bond, whereas things more in the middle of the periodic table will be covalent bonds with various degrees of polarity. Now, ionic bond is obviously very polarized, but covalent bonds are polarized as well. So if we look at this molecule that we talked about previously with carbon and chlorine bond, the chlorine will have the partial negative charge, whereas the carbon will have a partial positive charge. This Greek letter delta simply means little negative charge, so not the full ionic charge. And since there is a plus and a minus n in this bond has a dipole moment, which is denoted by this arrow, which has a plus, kind of a plus sign at the positive end, and then the minus is where the arrow is pointing to. Okay? Now, so clearly this bond is covalent non-polar, covalent polar, but is there any way to quantify that polarity or that propensity of an atom to engage into covalent polar or non-polar bonds? Yes, there is. And this property is called electronegativity. And so electronegativity is a measure of elements propensity to attract electrons. Okay? And let us look at some of these numbers so things will become a little bit more apparent. Hydrogen has electronegativity 2.2. It is not defined for helium because helium is unreactive. Lithium has 1.0, sodium has 0.9, potassium has 0.8, circle this value. Then beryllium is 1.6, boron 1.8, carbon 2.5, so getting higher. Nitrogen is 3.0, oxygen is 3.5, and fluorine here is 4.0. And you will see, as I finish this table, that this is the highest number in the periodic table. aluminum is 1.6, silicon 1.9, phosphorus, sulfur, chlorine 3.2, bromine 3.0, iodine 2.7. So first you can see that these values vary between 0.8 and 4.0. Don't ask me why these numbers are this way, because this scale is completely arbitrary. It's called the Pauling scale after Linus Pauling, who was a Nobelist, actually a double Nobelist in chemistry and peace. And this basically tells us that fluorine is the element in the periodic table which wants the electrons the most. So all bonds to fluorine will be polarized, and they will all have the negative end on fluorine. Potassium, on the other hand, is one of the elements in the periodic table which wants electrons the least. So again, all bonds to potassium will be polarized towards potassium with the positive end of the diamond. And this also enables us to look at our previous molecules. So carbon and chlorine, you see that there is a difference in electronegativity of 0.7 units. So carbon is 2.5, chlorine is 3.2, which means that the negative part will be on chlorine, the positive part will be on carbon.